The title of today's webinar is Techniques for Soil CO2 Flux Measurement. And before we get going with the actual presentation, we've got a poll question that we'd like to ask the audience. We'd sort of just like to get a feel for what kind of systems people are currently using to measure fluxes, whether they're home built or they're available from us or some other manufacturer. So Ashley's going to guide you through how to answer this, and then once we get some answers, we'll get going with the webinar. Thanks, Ashley, and thanks to our audience for answering all those questions. Those are interesting looking results. So let's get going with the topics that we're going to discuss today. I'd like to start by clarifying a little bit of terminology. We see a lot of times that soil respiration and soil CO2 flux are often used as interchangeable terms, but they're not really the same thing. When we talk about soil respiration, we're talking about the actual quantity of CO2 produced in the soil by biological activity. So respiration from microbes, soil roots in the soil. And when we're talking about soil CO2 flux, we're actually talking about the transport of CO2, the movement of CO2 from the soil atmosphere out into the bulk atmosphere above the soil. And when we talk about these things, we're typically quantifying this in terms of sort of a mole count of CO2 molecules per given area per time. So typical units would be micromoles per meter squared per second. So the technique that I want to start with is the gradient method. And in the gradient method, you deploy a series of CO2 sensors throughout a soil profile. And you'd measure flux by looking at the CO2 gradient across the soil. And taking this gradient times a soil diffusivity coefficient. So this coefficient describes the movement of CO2 throughout the soil, and ultimately getting a flux. The issue here is that it's very difficult to estimate this diffusivity term. D is a function of not only sort of the structure of the soil porosity, but it's also a function of the moisture content in the soil. Temperature of the soil gas, and so it's constantly changing while you're trying to make these measurements, so it leads to a lot of uncertainty in this technique. And in general, when we talk about a CO2 concentration gradient within the soil, we can often say that in the uppermost layers of the soil, the CO2 concentration is at its lowest, and it gets higher and higher as you move deeper and deeper through the soil profile. At least to a point. And that direction of that gradient is what this technique relies on. Well, here's a sample data set where the gradient method is just completely failed. On day 214 here, a rain event occurred. It saturated the upper soil levels. We know that CO2 has a much higher rate of diffusion in air than in water, so as we increase the soil moisture content up there, we've got more resistance to CO2 moving out of the soil. So we can think of that sort of like a capping event. And we added more moisture to the soil, so we've increased those respiratory processes that are actually generating the soil. So if we look on day 215 here, the CO2 concentration gradient's actually reversed. Now if we follow through the math for the gradient method, the equation that I showed in the last slides, well, that would suggest that there's a net flux of soil a net flux of CO2 into the soil. Well, we know that's just not the case. So a different approach would be to use a chamber-based measurement. And in a chamber-based measurement, you're covering over an area of soil and measuring what's going on with the CO2 concentration within the chamber. And there's two approaches to this. There's a steady state, or it's often called an open system or open approach. And there's a closed or transient approach to making chamber-based measurements. Well, in a steady state or an open system, you've got a chamber that covers over an area of soil. And the way to think about this is that you're constantly flowing a gas stream through that chamber. And what you're ultimately measuring is the rate of flow through the chamber and how that gas stream is modified as it passes through the chamber. So you can think about measuring a CO2 concentration of the gas before it enters the chamber and a CO2 concentration of the gas after it passes through the chamber. Now, the difference of those two times the flow rate divided by the area gives you a mass balance, and from that mass balance you get a flux. So the advantages of an open system or a steady state system is that, well, gas concentration inside the chamber is at steady state. And in the case of making soil CO2 flux measurements, well, what we're measuring here is a diffusive flux. And so the flux that we're measuring is a function of the difference in gas concentration between, in this case, the chamber headspace and the soil atmosphere. And so having a gas concentration of the chamber that's at steady state for any given flux is wonderful. And the assumptions are relatively simple. Basically, what goes in plus what's added by the flux equals what goes out. But there's some disadvantages to this measurement technique. Well, the first one is that you've got to know flow, and you've got to know it with quite a bit of accuracy, because whatever error you have in your flux or in your flow measurement, well, that propagates 1-to-1 in your flux measurement. Well, because you're measuring gas concentrations at two different points, say before the chamber and after the chamber, you have to do this with two different ergas. And because your flux is directly proportional to the difference between what those ergas are measuring, you need two really well-matched ergas. And one of the examples I like to give here is, say you have a flux that causes a difference between your ergas of 9 ppm. And the actual difference that you measure between your ergas is 10 ppm. So you have a 1 ppm error between those. That seems very tiny, but that's going to cause a 10% error in your flux measurement. One of the other disadvantages here is because you're actively flowing a gas stream through the chamber, typically at a fairly high flow rate. I mean, you need a turnover that's a couple times the chamber volume. It's very difficult not to create a pressure differential in the chamber. And one of the other things is that you're covering over the soil, so you're inherently disturbing the environmental conditions of the soil. You're affecting radiation balance on the soil. If the chamber's closed for a very long time, you might have an effect on chamber temperature, or soil temperature or soil moisture. So our other chamber-based approach is a transient or closed system. Similar to an open system, you would close over an area of the soil with your chamber, but rather than actively flowing a gas stream in and then exhausting it out, you continuously circulate the same gas stream through basically a closed system between an erga and a chamber. And you measure the change in CO2 concentration in the chamber headspace over time. Well, if you take a slope of this curve, the dc dt term in the equation shown here, and you know chamber volume and pressure during the measurement, temperature during the measurement, and area, well, you can compute a flux. The advantages of this system is, well, it requires really simple assumptions. You don't need a very fast analyzer. If you had 1 second response on the analyzer, that would be more than sufficient here. And depending on what your requirements are and how complicated a system you wanted to build, one of these things could be built very inexpensively, because all it requires is a chamber to cover over the soil and an infrared gas analyzer and a pump. The disadvantages are that you inherently disturb environmental conditions when you're making the measurement. Just like an open system that I showed you in the previous slides, with a closed system, you're covering over the soil. And just like with an open system, for different reasons here, it's difficult to have chamber pressure track ambient pressure. So now we've introduced the different measurement techniques. So let's talk a little bit about what the requirements are for making good chamber-based measurements. And so sort of our thesis statement here is that, when we deploy chambers, we need to know that these chambers don't disturb soil CO2 production or soil CO2 transport. I mean, this is sort of based on an inherent principle in the sciences. You don't want your measurement technique to affect what you're ultimately trying to measure.
Jason, I'm going to interrupt you with an audience question. The question I have is, I'm thinking of constructing a home-built flux system, as I have seen several published in the literature. What are the things I need to think about?
Well, that's an excellent question, Ashley. And a good lead-in to what we're about to talk about. So in the rest of the presentation, I'm going to talk about the requirements for chamber-based measurements. And these are all things that would be very important to think about when building your own home-built system. The other thing that will be really important to think about is how to treat water. A lot of people make the assumption that they can get away with just a standalone CO2 analyzer that doesn't measure water vapor. And that ignores some pretty significant physical properties that will, if ignored, will greatly affect the fluxes that you're trying to measure. So let's go ahead and move on with these requirements, and I think this will do a pretty good job of answering our customer's question here. There's really 5 criteria that we have to meet. The first is that our CO2 concentration in the chamber needs to equal the CO2 concentration in the air when we didn't have the chamber closed over the soil. And that goes back to this being a diffusive flux. So we can think about the flux being a function of the CO2 gradient, the difference in CO2 concentration between the soil and the airspace above the soil, times some conductance that describes the ability of that CO2 to move through the soil, and that ultimately gives you a flux. So if we want to know the flux that's going on when our chamber is not setting over the soil that we're trying to measure, we need to know that the CO2 concentration in the chamber equals the CO2 concentration of the air that would have been there. Well, not only can we alter the gradient driving the flux by having the chamber's CO2 concentration different, well, we could throw our chambers down and we can affect the CO2 concentration in the soil. And so we need to know that by deploying our chambers, we're not affecting the soil atmosphere. We need to know that pressure in our chamber is equal to ambient pressure. Ultimately, the flux that we want to measure is diffusive in nature, but if you created a pressure differential between the soil atmosphere and the chamber atmosphere, you could create a bulk flow, and that bulk flow is a confounding flux. We need to know that we have good mixing inside the chamber. So we need to know that all the gas in the chamber headspace is at the same concentration, because if it's not, those pockets of unmixed air can act as sources or sinks for CO2 and create another confounding flux affecting what you're trying to measure. And finally, we need to know that deploying our chambers has no disturbance to the soil moisture, temperature, radiation balance of the area that we're trying to measure, because these factors drive the soil CO2 production. Ultimately what we're trying to measure. So as I go through how you would address each one of these in a chamber-based measurement system, the example that I'm going to use is how we've addressed these things in the LI-8100 system. So not an attempt to sound like product placement here, but this is the system that we have the experience with, and so we're going to show how we've tackled each one of these using this system. So the first criteria, CO2 chamber needs to equal CO2 air. Well, what we're showing here on the figure is a plot of CO2 concentration in the chamber over time. And there's 2 lines fit to this. There's the black line shows a linear fit, and the red line shows an exponential fit to this CO2 to the CO2 concentration over time. So traditionally, when people have done soil CO2 flux measurements using closed systems, they've taken a linear fit to the data to estimate the dc dt term that I showed you in the equation before. Well, the issue here is by doing a linear fit, you're sort of taking an average flux over the measurement period. And that flux remember, is driven by the CO2 concentration gradient between the chamber headspace and the soil atmosphere. And ultimately, what you want to know is the CO2 flux when the chamber headspace is at atmospheric concentration. If you do a linear fit, you're always going to underestimate the flux at ambient concentration because the curve is inherently exponential in nature. I mean, if you were to allow this measurement to go on for a longer period of time, eventually the curve is going to even asymptote at the top because the chamber's CO2 concentration is going to come into equilibrium with that of the soil atmosphere. And so what we do in the 8100 is we do an exponential curve fit, and we take dc dt, the slope of the exponential curve, at time 0, and we assume time 0 is when the chamber concentration is at atmospheric concentration. And so here's an example of fluxes for the same curve using the different curve fit techniques. And what we see is that the linear curve fit underestimates the flux at atmospheric concentration. This is irregardless of the fact that, R squared for the linear fit is still very high. It's 0.99 something. So our next requirement is that we don't disturb the soil CO2 concentration. And we address this a couple of different ways. One of the things we use is a soil collar. And that's what's pointed to here with the red arrow. Basically, these are 4-inch or so sections of PVC sewer pipe that get inserted into the soil prior to making measurements by a day or so. And what the soil collar does is it provides us a surface that we can make a gas-tight seal to easily with our chamber. And it allows a stable platform for placing the chamber over the soil. So when we shove this collar in, we're pushing the collar into the soil, and we're creating essentially a bulk flow gas out of the soil. And it takes some time for that the CO2 flux to come back to normal after that. And when we set the chamber down on the collar, one of the other things we do is that the chamber is open. If you were to take a closed chamber and just sort of slam it down on a collar, there's a good chance you could cause a temporary overpressure in the chamber, and that could force gas back into the soil and suppress the flux that you're trying to measure. One of the other approaches that we use to not disturbing the soil CO2 concentration is that for our long-term chambers, these are actuated chambers. They're only closed when we're making a measurement, and we make a measurement for a short period of time. In the top figure here, we're showing the measured flux over time for a bunch of repeated measurements. And so in this first measurement, our chamber has been open. We let it close for 5 minutes, and we measure the flux. And that 512 ppm number is the initial CO2 concentration in the chamber. And we see that after 5 minutes of chamber closure, and 5 or 6 minutes later, the flux has come back to some value that's close to what we were measuring when we were just using a short measurement period prior to that. Well, a little while later, we let the chamber set closed for 10 minutes, and after 10 minutes, our chamber's CO2 concentration is 900 and something, and our flux is much larger than what it was, and it takes even longer to recover. And so the longer we let the chamber stay closed, the higher the CO2 concentration builds, and the longer it takes for the CO2 flux to recover back to pre-measurement levels after we've opened the chamber back up. And the reason for this is because CO2 was building up in the upper soil strata. And so we're altering the CO2 concentration in the soil. So we're altering the gradient that we're trying to measure. One of our other requirements is that pressure in the chamber is equal to ambient pressure. But one of the assumptions of a closed system is that pressure doesn't change during the measurement. Well, in a closed system, we're operating with a fixed volume. Typically, temperature is stable over the measurement period. That's actually another assumption of a closed measurement. And we're allowing gas to build up in the chamber. Well, if we're adding gas to a fixed volume under constant pressure, under constant temperature, the only way to maintain constant pressure is to have a pressure vent on the chamber. And traditional pressure vent designs were just straight tubes. And when wind blew across these tubes, it could act like a venturi, and it could cause either an overpressure or underpressure in the chamber, and that would cause a bulk flow of gas out of the soil and into the chamber. Well, in the 8100 system, our chambers use a different pressure vent. This pressure vent follows or applies the Bernoulli effect, where if we change the orifice diameter that a gas is flowing through, we change the speed of that gas. And so what this does is it allows us to have a pressure vent that's insensitive to wind. And so we always know that chamber pressure is at atmospheric pressure. One of our other requirements is that we need good mixing inside the chamber. And so for a closed system, we can apply a model that lets us predict CO2 concentration at time t for a given rate of change of CO2 in the chamber. And so using a system where we have our infrared gas analyzer, our pump, a sealed chamber, and a bottle of soda lime plumbed in line with the system. Soda lime is a strong CO2 sorbent, and as the gas stream flows through it, the gas stream going in one side is at whatever the CO2 concentration in the chamber is, and the gas stream coming out the other side is basically at 0 CO2. We can make some predictions of what the chamber CO2 concentration would look like at a given time, assuming a certain level of mixing inside the chamber. And so here we show two curves in red that sort of bracket perfect mixing in the chamber by plus or minus 10%. And the curve in blue is what was measured using the setup described in the previous slide and one of our long-term chambers and a flow rate of 1.5 liters per minute. And what we see is that the blue curve falls right in the area where we would expect if we had perfect mixing inside the chamber. So our final requirement is that we don't disturb soil moisture, temperature, or radiation balance. So one of the ways we do that for our long-term chambers is that the chambers are actuated and they remain open when we're not actively making a measurement. One of the other ways we achieve this is that the actual apparatus of the chamber, the platform that it sets on, is perforated, and this allows light and moisture to reach the soil surrounding the soil collar. You got to remember our soil collar is only going down into the soil a centimeter or two, and soil is a continuous medium, and so what's going on outside the collar can certainly affect what's going on inside the collar. And so both in our 101 version chambers and our 104 chambers, we use a perforated base plate. This sort of wraps up what we wanted to say about different techniques for soil CO2 flux measurement and what we wanted to say about the requirements for chamber-based measurements. As Ashley pointed out, this was the second in a series of 4 talks. And in the next talk, we will be discussing sort of the advantages of the LI-8100A system. We'll be following that talk with one on collecting and quality control of soil flux data sets. And then if you have any questions that come up after the webinar, please direct them to either myself or our principal scientist, Lukong Zhu.
Thanks for the presentation, Jason. I have just one audience question for you, and it is, Jason mentioned water vapor in answering a previous question. I'm not sure I understand why water vapor would matter when measuring CO2 flux.
Well, that's an excellent question, Ashley, and I suppose I didn't give a very good answer or very good description of why that matters in answering the previous question. Well, water vapor comes into play when we're measuring CO2 flux in 2 ways. In the first way, for most of these systems, we're measuring CO2 concentration using an infrared gas analyzer of some sort. And the way these gas analyzers work is that they provide a light source, and there's some sort of optical filtering that narrows that light source down to a set of wavelengths that correspond to a region of the electromagnetic spectrum where CO2 molecules absorb radiation. And so we talk about absorption bands and absorption lines. And so the amount of absorption that CO2 absorbs at one of its absorption bands is a function of, it follows Beer-Lambert law. And so it's a function of gas density in the mixture, and it's a function of the optical path length. But it's also a function of temperature and pressure, and a function of all the other gases in the gas mixture. And so the way we use a LI-COR infrared gas analyzer as an example here. We make a broadband measurement of CO2 at around 4.2 micrometers in wavelength. And when we do a calibration, we do all our calibrations in a mixture of dry, of CO2 mixed in a balance of dry air. And then we measure water vapor, and we make a correction for the band broadening effects of water vapor. So as water vapor increases in the mixture, it increases the absorption of CO2, infrared absorption of CO2. And if you don't correct for it, the measurement device has an inherent error. And the other way that it really gets you in making a CO2 flux measurement has to do with the ideal gas law. And we've got two competing fluxes going on here. We've got CO2 flux into the chamber, and we've also got water vapor flux into the chamber. And our chamber is staying at constant pressure because we have a pressure vent on it, and that's an assumption of a closed system. This also happens to be an assumption of an open system, is that these are at inherently constant pressure. And so as we have water vapor moving in, it's physically displacing CO2. And so the larger the water vapor flux into the chamber, the more suppressed the CO2 flux is going to be if you were just measuring CO2. And so you're going to have an underestimation of the flux. And the way we treat this in the 8100 is we compute all our fluxes using a dry mixing ratio. I skipped over this when I was talking about our exponential curve fit, but I showed C prime as the variable for CO2 concentration that we were using. And that prime denotes that it's a dry mixing ratio. So it's the theoretical concentration of CO2 if the air in the chamber was completely dry and free of water vapor. And so if you don't measure water vapor, on the one hand, band broadening is going to make your analyzer overestimate the CO2 concentration. And on the other hand, dilution of water vapor by moving into the chamber is going to cause you to underestimate your fluxes. Maybe sometimes this doesn't matter. If you're making flux measurements on desert soils where there's very little water vapor flux into the chamber, well, the dilution effect's not going to have any effect. But if you're measuring on wetland soils, the water vapor flux into the chamber can be a couple orders of magnitude bigger than the CO2 flux into the chamber. And the dilution correction on its own may be the same size or larger than the CO2 flux that you're trying to measure. Well, I think that sums up the answer to the question. Anything else, Ashley?
No, that's it, Jason. Thanks. And thanks to our audience for submitting your questions. And thank you to our panelists for answering them throughout the presentation. Our panelists will stick around until all of our audience questions have been answered. This concludes our replay of techniques for soil CO2 flux measurement. We will be hosting replays of the next 2 webinars in this series in the coming weeks. I've posted a schedule on your screen. Last week's replay is available from our webinars page, www.licor.com/env/webinars. We hope you can join us for the remainder of this series. Now, any questions you have that have not been answered by our panel can be directed to either Rod or Jason, and their contact information is on the screen as well. So thank you for joining us today, and we hope that you enjoyed the opportunity to watch a live replay of this event. Please let us know how things went by filling out our post-event survey when you close out of this webinar.